All right, welcome everybody to our weekly machine learning seminar. This is the first seminar in the new academic year, and we'll have a pleasure to have a presentation from Alena Kopanicakova from the Brown University in USA, who will have a talk on multi-level training of deep residual networks. Please go ahead, Alena, just present yourself and then this virtual floor is yours.
Okay, so thank you very much for invitation and also nice introduction. Today I will present work which has been done basically on end of my PhD. So I started working on this topic while I was writing my PhD thesis, which in my stay in Lugano, and then I continued during my postdoc. And now recently, during this summer, I switched to Brown University, so I will still present work which has been carried out during my stay in Lugano. So in particularly, this talk will be about multi-level training methods for deep residual networks. So this talk will have three main parts. So in beginning, we will do a very brief introduction to supervised learning and with particular focus on deep residual networks. Then I will do some very brief introduction to standard training approaches, and then we will also discuss some more novel approaches which are not very common in machine learning community. And then at the end, we will discuss some multi-level strategies based on multi-level trust region methods. And here we will discuss some basic algorithmic components, and also I will show you some numerical results. So let us directly start. So we start with brief introduction to supervised learning. So as you all know, field of supervised learning is very popular nowadays, and this type of methods are used in various areas of computer vision, speech recognition, but also in physics and medicine. I think I would have to deeper to try to find area where deep learning or supervised learning is actually not used nowadays. So in general, idea behind supervised learning is to uncover relationships hidden in some data set D, which contains P samples, and each sample consists of some input features. And then we have also some desired output. For example, in terms of classification problems, this output would be some labels. So in general, supervised learning is associated with two types of problems. So we have forward problem, where for our given input feature, our goal is to predict its output. And this is done by using some parameterized model FM. And this type of model which we use will depend on type of network architecture which we employ. So it can be simple single layer perceptron or some very deep network with a lot of layers. So this really depends on type of network you would like to use. Then in addition to forward problem, we have also inverse problem, where for a given data set D, we are looking for optimal set of parameters theta, which could parameterize our model FM. And we find these parameters by means of this minimization problem. So our goal is to minimize loss functional, which takes into account misfit between output of our model, so our prediction, and our desirable output, which is prescribed in dataset D. And of course, we have to take into account some regularization term in order to make sure that our problem is well posed. So in this work, we will focus on one particular type of network architectures. So our model will be defined in following way, where we have some forward propagation function, which will follow by affine transformation of features, and then we have some also hypothesis function. Here, in terms of ResNet networks, this forward propagation can be defined in recursive manner, where output on k+1 layer is defined as sum of two terms. So we have output on a previous layer, epsilon k, plus some nonlinear transformation of features. And this nonlinear transformation of features is often called nonlinear residual block. There are many ways how these nonlinear residual blocks can look. So for example, we can have a simple single layer perceptron, so affine transformation of features followed by some nonlinear activation function, but it can be also something more complex, as more common in ResNets, which are used for image classifications, where we have some convolutions followed by batch normalization and then some activation function, and this can be repeated multiple times. So in this work, we will rely on a dynamical system viewpoint, which was initially introduced in 2017, I believe, where it comes from very simple observation that if we take equation of forward propagation through the ResNet and we append some small scalar, let's call it delta t, in front of our nonlinear function f, and reorder whole equation, we end up with following formula. Now, if you look into this formula, you notice that this term looks pretty much as a forward Euler discretization of following initial value problem, where now we work with some time interval from 0 to capital T, and we also employ some time-dependent control variables and state variables. Of course, initial state is defined at time 0, and final state or network output, as we will see later, is defined at final time, so capital T. So using this simple observation, we can transfer our supervised learning problem into continuous optimal control problem. And here we are still minimizing our loss functional, but now we also introduce some constraint, which is this ODE, which we obtain in previous slide. And this constraint will enforce a particular type, it will enforce how we obtain a result of our forward propagation. So using this dynamical system viewpoint is fairly nice, and I think it also managed to open doors to a lot of new research areas. For example, employing different discretization techniques for this time derivative gave rise to different and also novel network architectures. Also, employing this viewpoint allowed to enable parallelization across layer by employing some parallel in time strategies. And in this work, we will mostly focus on enhancing training process of ResNets by taking into account this dynamical system viewpoint. So since my work is mostly on this enhancing training of processes, let us briefly point out some properties of underlying minimization problem. So first of all, you can see that our loss functional has finite sum structure. So you can see that we sum over all misfits across all samples in our dataset. And this will be later explored to build some maybe more computationally efficient solution strategies. We also know that our underlying loss functional is non-convex and our energy landscape is very rough. So here we have just simple example, which was reported in this paper by Lee and coworker in 2017, where basically they just try to demonstrate how energy landscape of a deep network looks. And as you can see, there is a lot of local minima and also saddle points, flat regions. So it's very difficult to basically construct some solution strategy which can converge to reasonable solution strategy, to converge to reasonable solution. Okay, at the end, I would like to point out that cost of evaluating this loss functional depends on two major factors. So first of all, it depends on size and properties of underlying dataset. So how many samples we have in our dataset, and also size of input features. And then we also have properties of models. So how many parameters is our network and what is our network architecture. So traditionally, this minimization problem is carried out using some line search framework. So parameters of our model or network are updated by using some search direction sk, which is scaled appropriately by using some learning rate or step size alpha k. There are two basic methodologies how to obtain this search direction. So I think the most standard is to use batch approach, where search direction is constructing using all samples in our dataset. So for example, if you decide to use first order optimization method, then our search direction would be obtained as a negative gradient evaluated using all samples in dataset. So then we know that our search direction would be direction of descent at any point. And we can build a convergent iterative scheme by simply choosing line learning rate sufficiently small. Alternatively, we can use some stochastic approach where our search direction is constructing using only single randomly selected sample from our dataset. So for example, here again, using first order approach, our search direction is constructed as negative gradient, but now evaluated using just this JK sample. And you can see that now we have to be slightly more careful how we construct our iterative method, because our search direction is in general probably not direction of descent at any point. But since our stochastic gradient is unbiased estimate of our gradient, we can drive our iteration scheme to converge, but we have to be careful how we choose our learning rate. And in particular, we have to make sure that our learning rate decreases to 0 to actually reach some sort of solution. What is important if we compare these two approaches is that you see that in batch methods, our iteration cost depends linearly on number of samples in our dataset. Well, in terms of stochastic methods, our iteration cost is independent of number of samples in our dataset. So these methods are very much more effective in terms of iteration cost. What is often also done something in between, which is called mini batch methods, where instead of using just single sample, we use small subset of samples in our dataset. And in general, in this talk, when I will be talking about stochastic methods, typically I have on mind mini batch methods. So this is generic line search framework, which is often used in machine learning. But in this work, we will focus on slightly different approach, which will be used based on trust region method. So since trust region method is slightly more involved, let me first introduce standard batch or deterministic trust region framework, and then we will discuss how to adjust trust region method to other settings. So in general, trust region method was designed to solve non-convex minimization problems. And the idea behind a trust region method is to, on each iteration, to construct some model MK, and then solve this model in order to obtain a search direction. So this model MK can be constructed in various ways. So for example, as second order Taylor approximation of our objective function around current iterate. But there are also other approaches. Importantly, you see that this model is just approximation of our objective. So we cannot trust it blindly, but we trust it only in certain region, and we will call this region trust region. And the size of this region will be controlled by this trust region radius delta. So as I said, in each iteration, we will minimize this quadratic model in this case in order to obtain search direction. But importantly, you notice that this minimization is subject to so-called trust region constraint, which basically controls how big our correction can be. So as soon as we solve this trust region subproblem and obtain our correction, trust region method has to evaluate whether this correction is suitable. And this is done by using this trust region ratio rho, which compares decrease in objective function with respect to decrease or predicted decrease in model MK. And we accept our correction only if there is decrease in objective function. Otherwise, correction is rejected. Of course, we have to also adjust trust region radius. So if our correction was rejected, then we make our trust region smaller. So our next correction would be smaller. So basically, this constraint will become tighter. Alternatively, if our correction was very good, we trust our model and we can increase trust region radius. So now, if you have a look at this algorithm, you notice something very important, that there is no need for user to specify learning rate, because trust region algorithm automatically adjusts by itself learning rate, and this is done internally by means of this trust region radius delta. And I believe this is the most appealing feature of trust region methods in terms of machine learning applications. Nevertheless, this algorithm is fairly computationally expensive because we have to build this model and solve trust region subproblem, and then also evaluate or check convergence. So this can be fairly expensive. So in this work, we will try to decrease computational cost of this trust region method using two complementary ideas. So first of all, we will put our trust region method into stochastic settings, and then we also employ multi-level variant of trust region method, in order to decrease computational cost even further. So first, let us have a look into stochastic variants of trust region method. Here, first of all, I would like to remark that building stochastic trust region method is very much more complex than building stochastic line search method. And this is mostly due to the fact that we are checking convergence on each iteration. As we saw in line search methods, we can use subsample information to evaluate Hessian or Hessian approximation, and same for gradients. But this will still not decrease computational cost of our method deeply, and this is due to the evaluation of this trust region ratio. We can, however, decrease computational cost by also considering subsampled information. But as soon as we do that, we might lose global convergence properties of deterministic trust region method, and this is due to the fact that decrease, which we observe on mini batch loss, does not necessarily imply decrease in global loss. So what we will do in this work, we will try to preserve global convergence properties of trust region method by adaptively increasing accuracy of our estimates of objective function and also gradient and Hessian or Hessian approximation. Okay, so this is stochastic. This is quick look into stochastic variants of trust region methods. And now let me talk a little bit about multi-level methods. So for those who are not familiar, these multi-level methods were initially introduced in numerics to solve partial differential equations, and they become quite popular. This is mostly due to the fact that they are of optimal complexity and scalability. And they were initially designed to solve partial differential equations which were elliptic, but later these methods were extended also to nonlinear systems of equations. So idea behind multi-level methods is to build some solution process which contains two complementary techniques, which is nonlinear smoothing and nonlinear coarse grid solve, where nonlinear smoothing is removing high frequency components of the error, while coarse grid solve is removing low frequency components of the error. So in this work, we will be looking on nonlinear multi-level minimization methods. These methods do not assume any existence of discretized PDs, so they are very much more generic than initial multi-level methods, which were designed just taking into account discretization of PDs. And there is many nonlinear multi-level minimization techniques around. I think they can be mostly distinguished based on the type of globalization strategy they use. So we have multi-level line search methods. I think the most prominent example is MGOB method. And these methods are more suitable for convex objective functions. So in this work, we will focus on multi-level trust region methods as they were originally designed to solve a non-convex minimization problem. In particular, we will adapt multi-level trust region method initially developed by Grato and coworkers, and we will adapt it such that we can use it for training of deep residual networks. Okay, so let me just give you a quick introduction or sketch how such a two-level multi-level trust region method can work. So if you recall my previous slide, single-level trust region method worked in following way. On each iteration, we constructed some model, and then we minimized this model in order to obtain some search direction, and then trust region method checked whether this search direction is meaningful or not. And for the moment, we will refer to this step as fine level step. Alternatively, we can decide to construct some coarse level model as approximation of our loss functional and minimize this model in order to obtain some search direction. This coarse level model can be constructed in many ways. In this work, we will construct this model by reducing dimensionality of our problem. So by considering networks with fewer number of parameters on coarser levels. In order to do so, since our coarse level models will be constructed using this dimensionality reduction technique, we will have to also devise some sort of transfer operators to move certain quantities between different levels of multi-level hierarchy. For example, we will employ projection operators, restriction operators, and also interpolation operators. Traditionally, one would iterate between fine level and coarse level step, which would give rise to some sort of V-cycle type of algorithm. Of course, we can also define coarse level models of coarse level models, which would give rise to full multi-level method. So here is just simple bullet points of 3 main ingredients which are needed to be provided such that we can construct our multi-level trust region method specifically tailored for ResNet. So first of all, we have to build some hierarchy of auxiliary low-cost objective functions. And as I said, we will be doing this by employing some dimensionality reduction techniques. And then these objective functions will be used to construct our coarse level models H. So basically these models. Of course, we also have to incorporate transfer operators. And at the end, we have to make sure that we preserve convergence properties of single level deterministic trust region method. So first, let us start with multi-level hierarchy and transfer operators. So multi-level hierarchy and transfer operators have to be built with idea or information regarding of our problem. So here we focus only on training of ResNet. So we consider our continuous optimal control problem, which we obtain by taking into account dynamical system viewpoint. We know that in order to solve this problem numerically, we have to discretize our ODE. So here we will consider some time interval from 0 to t, and we consider one-dimensional mesh, which we discretize using uniform time steps, and then we use this time interval for discretization of our ODE. Here we try to mimic ResNet architecture, so we just use simple explicit Euler scheme, and using this approach, we will obtain discrete minimization problem where this constraint just imposes ResNet architecture, but now we have to be careful and we have to take into account this delta t, which is our time step. Just for you to have a better idea, now each time point in our time mesh will correspond to one particular layer or residual block of our network. We can also decide to refine our time mesh, for example, using uniform refinement, and this will give rise to minimization problem, which will incorporate network with twice as many number of layers as previously, and so on and so on. So we can perform this step recursively, which give rise to multi-level hierarchy of minimization problems, which internally employ ResNets with different depths. What is nice about this approach is that time is basically just one-dimensional quantity. So we can transfer data between different levels of multi-level hierarchy just using, for example, simple linear interpolation in 1D. So now let me give a comment about how to construct coarse level models using these minimizations problems which we just constructed. So on each level, we will construct coarse level model as a sum of two terms. So first term is our model discretize is our loss function obtained by discretizing on particular level, and then we have also correction term. Here we focus only on first order correction term, where is this delta G term, and this delta G term is obtained as difference between restricted fine level gradient, which was evaluated at current fine level iterate, and initial coarse level gradient. So employing this delta G term, we can make sure that first coarse level correction goes in direction of restricted fine level gradient. And moreover, we can ensure that if correction which we obtain on coarse level is descent direction on a coarse level, it will be also descent direction on a fine level after its prolongation. So basically this relation holds. And this is very important in order to ensure convergence of any multi-level method, not just multi-level trust region method. Okay, so in addition, some comments on how to preserve convergence in terms of trust region settings. So there are several important points here, just highlight. We will have to make sure that correction, which we obtain on coarse grid and then prolongate to final level, the size of correction which we obtain on coarse grid and prolongate to final level is bounded, and this bound is provided by fine level trust region radius. And every time we prolongate coarse grid correction, we will also measure its quality. And this will be done by using this multi-level trust region ratio rho, which is defined by comparing decrease in a fine level model with respect to decrease in coarse level model. And of course, we will accept prolongated coarse grid correction only if there is decrease on fine level. Otherwise, our correction has to be disposed because it does not improve our fine level model. So using all of this, let me just give you a demonstration of first numerical result. So here I consider classification problems using ResNets, where residual block is just simple single layer perceptron with dense, basically with dense layers. And we consider 3 different datasets, namely blobs, smiley, and spiral. And these datasets are generated in very simple way. So there are some particles in 2 or 3 dimensional space, and they are assigned to different classes based on their location. So for blobs, we have, I think, 10 different classes. For smiley, we have 4 different classes. And for spiral, we have 6 different classes. And then we measure computational cost of single and multi-level trust region method, which is required to train but we also perform this experiment with increasing refinement level, so with increasing number of layers, So as you can see, for example, from this line, that as we increase number of layers in our network, single level trust region method has problem to converge, while very much opposite behavior is detected for multi-level trust region method. So as we increase number of levels in a multi-level hierarchy, our relative computational cost is decreasing, and this is mostly due to the fact that we are outsourcing all heavy computational cost to coarser levels, which are very cheap. So overall computational cost is decreasing. So here I just have a simple example how prototypical convergence behavior of single and multi-level trust region method looks for training of this dense ResNets. So on left side, we have single level trust region method. So as you can see, our objective function is initially decreasing, as we would expect. Decrease is monotonic, so everything seems to be working. But then we encounter some region where our decrease in objective function is very slow. So we probably encounter some plateau region. And we are stuck there for almost 400 iterations or epochs. And then eventually we get out and our method converges. You can see that if we employ multi-level variant of trust region method, we somehow overcome this difficulty of getting stuck, and method just converges in very much more efficient way. So now let me also tell you how to incorporate single and also multi-level trust region method into stochastic settings to decrease computational cost even further. So here we will start by considering some small mini batch. And as our training will progress, we will be adaptively enlarging mini batch size, and eventually we will end up with deterministic method. So algorithm which we employ is called a dynamic sample size strategy, and it has 2 phases, local and global. So in local phase, we have our shuffle dataset, which we split into any mini batches, and then we pass through all mini batches in sequential manner. And every time we are in new mini batch, we either perform one step of trust region or multi-level trust region method. And as soon as we pass through all mini batches, so as soon as we perform one epoch, we switch to global phase, where we basically measure quality of accumulated mini batch corrections. So here in particular, this quality is measured by means of this global trust region ratio, where we compare decrease in a global objective function. By global, I mean objective function evaluating using all samples in the dataset on beginning and end of epoch. And this is compared against average decrease in local objective functions. And here by local, I mean objective functions which were evaluating using just mini batch information. And as previously we saw, we accept our correction only if certain condition is fulfilled, otherwise correction is disposed. But here we not only dispose correction, but we also increase mini batch size because we believe that our correction, because we believe that number of samples in a dataset is not, or number of samples in mini batch is not sufficient to represent information contained in the full data set sufficiently well enough. So as training progresses, we end up with some deterministic method, and at this point we recover basically global convergence properties of single or multi-level trust region method. So here I would like to demonstrate how such a multi-level method works on convolutional ResNets, and in particularly we will employ these ResNets for image classifications task. So we will employ residual blocks which are common in literature. So we will have some convolution followed by batch normalization, then ReLU, and again convolution, batch normalization, and ReLU. What is important here, each stage will consider different number of, for each stage we will consider different number of filters. So stage 1 we will have 60, stage 2 32, and then 64, and every time we change stage we will also downsample our image by means of average pooling operation. I think what is important to mention here that each stage will have associated separate dynamical system. So basically we will build multi-level hierarchy and transfer operators separately for each stage of our network. So just to give you a simple example, here I have a two-stage ResNet and I demonstrate how to assemble prolongation operators. So you can see here we just use simple piecewise constant interpolation, but you see that data is just transferred from coarse level to fine level, but there is no transfer of data between different stages. So all information is contained within one particular stage. So here, let me present some numerical results. So here we consider 3 different types of datasets, in particularly fashion, cipher 10 and cipher 100. So fashion dataset contains cloth images which are grayscaled, and I think they were collected by using Zolando webpage. And then we have cipher 10 and cipher 100 datasets, which contains colorful images which belong to 10 different classes and 100 different classes. And we train our convolutional ResNets using 6 different types of optimizers. So in particular, stochastic gradient descent, Adam, then single level trust region method and multi-level trust region method. For both trust region methods, we consider approach where we only employ first order derivative information, so gradients. Then we also consider approach where we approximate Hessians by means of limited memory LSR1 method. And as you can see from obtained results, methods which incorporate some curvature information, such as Adam and trust region methods which employ LSR1 strategy, tend to overtrain. So although they are efficient, we are not able to reach state-of-the-art accuracy. In contrast, methods which employ only first-order information, such as stochastic gradient method and trust region CP and RMTR CP, manage to reach comparable and state-of-the-art accuracy. It is also important to notice that by employing multi-level variant of trust region method, we are able to decrease relative computational cost close to by factor 4, for example, for cipher 100 example. So just to have more content results, here we report best validation accuracy and computational cost, which we computational cost for all 6 methods, and we performed this experiment with increasing number of layers in with increasing refinement level, so increasing number of levels and layers. So as you can see, as we increase number of layers in our ResNet, we can achieve better validation accuracy. So this basically justifies a reason why we use deeper and deeper networks. But you can also see that stochastic gradient methods requires pretty much same computational cost to train all of these networks. Then if we look again to multi-level variant of trust region method, we see that we still can manage to achieve same validation accuracy, but our computational cost is decreasing with number of layers. So this is very similar to results which we saw in previous slides. Here I would also like to point out that by employing multi-level multi-level method, we managed to reduce variability of our results compared to single-level methods such as stochastic gradient. And maybe at the end, one more remark, that multi-level trust region method did not include any hyperparameters which had to be tuned, while in contrast, for stochastic gradient method, we had to find appropriate learning rate and also weight decay parameters. So this computational cost is actually not all computational cost which was involved to obtain these results. So with this, I'm almost done with my talk. I would just like to include one more slide, which about development of multi-level methods for transformer networks. This is something on which we started working recently because we were just interested to see whether this dynamical system viewpoint extends to other networks than ResNet. So as probably everybody here knows, transformers are state-of-the network architectures which are used in natural language processing, and recently it has been shown that they can be also interpreted as forward Euler discretization of some ODE, where these residual blocks are now way much more complex. So they consist of some attention mechanism, which is some nonlinear transformation, and then this is followed by some small feed-forward network, and there are also some internal shortcut connections. So these residual blocks are way much more complex, but nevertheless, we can use dynamical system viewpoint to build some multi-level methods. So here is just simple example on morphology classification task where we compare Adam with multi-level variant of ADA method. Here, our multi-level variant of ADA method is fairly simple. So we just use multi-level hierarchy to adaptively initialize weights in our network. But you can see that even employing this very simple strategy, we managed to obtain same validation accuracy, but at decreased computational cost. So in particular, time decreases by a factor of 2. So with this, I would like to conclude my talk. So today I mostly presented results from this paper, which has been just recently published. But in general, if you are interested in other multi-level or domain decomposition techniques, you can find some other approaches in other related literature. So thank you for your attention. And of course, if you have questions, please ask.
Thank you so much, Alena, for a great talk. It was very interesting to me, and I believe that it was interesting to many other people in this room. So I'm opening this discussion part. So whoever wants to ask, just either switch on your mic and ask, maybe perhaps your camera, or you can raise hand if you like. I mean, it's up to you. I have some questions, but I can see that Damian has his microphone on, so maybe he can be the first. There is a Sora raising hand.
Yeah, but
okay.
Damian can go first.
But I'm not sure if Damian wants to start. Okay, I don't know. Sora, you started talking, just let's start.
Okay, Alena, thanks for the talk. I think probably I missed this point you might have covered, but I just wanted to know. So you talked about this restriction and prolongation operations. Are they simple pooling operations, or you also have some sort of learning involved in them?
No, there is no learning involved. So you can employ, for example, for interpolation, you can employ piecewise constant approach, where you basically just copy these parameters to layer which would be corresponding to same time step, and also which would be corresponding to time step which has been obtained by refinement. So let me see, maybe I have a better picture. So for example, if you have layer corresponding to this time step, you would just copy parameters which are associated with this layer to layer above, and also here. So this would be piecewise constant approach. You can also do piecewise linear approach, where parameters of this layer would be computed by averaging parameters of this layer with parameters of this layer.
Okay.
But there is no learning involved. This is basically, these transfer operators are prescribed beginning of your training process, and you just keep them constant.
Okay, thanks.
Sorry. So just to follow up, question. May I? These are like these operators are the knowledge transfer operators. So these are not the weights of the new, or they are nodes of the neural network. So these are not the part of the neural network.
No, so basically
structure. Yeah.
So transfer operators are not part of network, but they are used to transfer parameters of the network, and also gradients, also gradients.
Okay. Thanks.
And because I saw that your main application was to solving some PTEs or time evolution problems, but can you possibly apply a similar approach to some unit architectures, for instance, when you have several levels of coarse-grained layers, and then you have this upsampling, and can you combine this concept with these architectures of neural network, or it is something completely different what you are doing here?
To be honest, I have not tried, and also did not think about using unit, but maybe you can combine, but to be honest, I don't know, because I didn't try. I just know that a lot of people like to interpret unit as multigrid by itself, or some sort of multigrid. So it would be actually interesting to see whether you can combine different approaches, but yeah, I don't know.
And also, may I have another question?
Yeah,
since
sure.
I can not see or maybe Onkar will be first. Okay, I will save it for later.
Jakub, no, go ahead if you want to ask a question. That's fine.
No. I have a separate question, so
okay,
it can go after yours.
Alena, thank you for the really nice talk. It was really interesting, actually. I just have one question. How do you define the size of the region? How do you know which delta to choose? How it happens? How...
So I would say there are two ways how to choose this delta t. Okay. First, very simple. You try to stay as close to original ResNet as possible. So you choose this delta t to be 1 on coarse grid, and as soon as you define it, will become delta half, delta quarter, and so on. So this is the simplest approach. Other approach, you can do some stability analysis to see at which point or how to choose this delta t so your coarse grid is actually not exploding and it's still having good representation properties and so on. But majority of people choose it based on whatever works. There is also alternative approach where you can learn this delta t on coarse grid. Okay. And then, once you learn this delta t, so it would be just another parameter which you have to learn for. And once so
so this is something like a hyperparameter which you have to...
Yeah, so this would be then hyperparameter which you have to find or learn. And then as you start refining, you would, of course, adjust based on your refinement strategy.
Okay, because that seems to be important parameter which affect your solution, right?
Yes, actually, if you choose this delta t to be very large, then your method will not converge because your explicit Euler will become unstable and your network just starts exploding. So you have to be actually very careful here. Yeah. So this is very good question.
To the learning rate thing as well. Means in learning rate, if you consider it higher, then it explodes.
Yeah, and in particular here you see that this delta t has also some sort of normalization effect because it's scaling this nonlinear transformation. So yeah, I think there is even correlation between how to choose this delta t and learning rate together.
Thank you very much. It's really interesting. It's really interesting work.
Thanks.
Vo, please go ahead.
Yeah, thank you for your presentation, Alena. I would like to have a question about the choice of the optimizer. In here, you can see you have the example of ADAM, stock HGD, and also the limit memory BFGS. And then I remember that usually limit memory BFGS will be the second order of optimizer, so it required quite a lot of computational effort. So for your approach, you approximate the loss for function, the objective function is an approximation, so it will push this second order optimizer will be faster, or it still be the same level of computational costs?
No, computational costs will be higher.
So
Definitely higher per iteration. You can make it almost negligible, but it's definitely going to be higher. And so maybe I have one slide which I actually skipped. So typically these Hessian approximations are computed by using this memory of second pairs. This pair is basically your search direction, and then difference between gradients which are evaluated before and after taking your search direction. And your cost of Hessian approximation will basically depend on choice how many second pairs you decide to store. So based on this number n. So this will heavily influence your computational cost. And then there are some techniques how to decrease computational costs. So for example, if you do just a naive approach, you have to evaluate these gradients on beginning and end of each mini batch, which is quite computationally costly because once you evaluate this gradient using updated parameters, you basically just trash this gradient, consider to next batch, right? So then you can decrease computational cost by imposing some overlap in your between samples in different mini batches, and then evaluating this term epsilon or computing these gradients just on this overlap. And if you choose this overlap to be sufficiently small, let's say 10% of your samples in mini batch, then computational cost of computing this Hessian approximation can go really down. So you can do certain tricks to decrease computational cost of Hessian approximation strategies.
And the second question is, by using this method, we can ignore the learning rate, but we also introduce the delta t, the truth region parameter. So it's kind of like we ignore A, we introduce B. So is it better in terms of for the user? I mean, for the user.
Yes, because basically, let's say you pick some delta t. I don't know. Let's say I don't know how to choose it, so I just choose it delta 0 to be 1. Then what happens in trust region method during first few iterations, if this delta is too big, trust region algorithm will just adjust, so it will shrink this delta t automatically. So user doesn't have to do anything. You just have to wait for algorithm to adapt and adjust. So okay, maybe 2 iterations will be somehow useless because you will be rejecting your steps and shrinking your delta. But after this algorithm catch up, and this typically really takes just 2-3 iterations. And this is very much more effective than training, I don't know, ResNet with 50 different learning grades.
Yeah. Okay, thank you very much.
Okay, so maybe now I will allow myself to ask question. I'm not sure if I got the idea correctly and if my question will make sense. But when you are operating on this various level of course graining, do you or can you do this in parallel, or you need to apply the staggered scheme in which you first apply the training step on the course level, and then you transfer the knowledge to the finer level and yet finer and so on so forth, and you probably need to have some back propagation of some information to the coarser level. Is it
Yeah.
which version do you use, and are the other one is the other one also applicable, like a parallel?
So for the moment, I use this sequential version in a way. So basically, my training starts on the finest level. So using a network, the deepest network, then I will transfer a few parameters. So for example, initialize parameter of Cursor network, also transfer some gradients and so on, then do training or Cursor networks, and then transfer corrections to update parameters of final networks. So in this way, you are right, algorithm is kind of sequential. What you can do in parallel, you can evaluate gradients and also loss function in parallel, especially in later stages of training, because as we progress, our mini batches are bigger and bigger. So you can happily parallelize over a number of samples. But as implementation of this cycle is currently performed in a very sequential way, that is true.
I see. All right.
You could maybe extend to additive version, but then you have to adjust a lot of stuff in terms of in terms of how you preserve convergence properties. So, for example, how you make sure that corrections which you collect by solving in different processor and also different levels will basically sum up such that size is together controlled by this trust region radius. So I think this would be very much more difficult to do. And there is, for the moment, theory missing how to do this to preserve convergence. So yeah.
I see. Okay, thank you for your answer.
Thanks.
So I don't know if there are any more questions. If not now, I think everybody can contact you offline after the presentation,
definitely.
especially the ones that couldn't make it now in live, and maybe they will listen to the presentation later. So again, thank you very much, Alena, for
thanks
this
for
very
invitation
nice presentation and for showing us this approach. And thank you everybody for your attention and for the discussion. And let me invite you for the next week for another presentation on our machine learning seminar. Have a good day, Alena. And
Bye,
have a
everybody.
good evening to everybody.
Thank you. Bye-bye.